Hi, my name's Larisa Sawyer. Thank you for coming. I'm here to tell you about some of the interesting work we've been doing at 2 Sigma, building a distributed time series analysis framework on top of Apache Spark. A little bit about myself. My background is in applied math and computer science, and I've worked in finance for the past 10 years. Now I work at 2 Sigma Investments, where I've been for about 3.5 years. At 2 Sigma, our mission is to discover value in the world's vast sea of data and use it to create investment strategies that benefit real people. We harness data from around the world and apply cutting-edge technologies and scientific research, and we come up with rational trading algorithms that we use to ultimately predict the future of what's going to happen in the stock market. In this talk, I'll describe one of the tools that we've built over the past couple years, which we've been using to study our data. We are able to optimize on Spark's already fast framework because we know that all the data that we're interested in is what's called time series data. So a time series is any observation, event, or data point ordered or indexed by time. So some typical examples that we think of are stock market prices, or the weather around the world, maybe the height of an average human in America, or comparatively, my height. The list goes on and on. We can think of cost of living, presidential polls. You could argue that really everything can be expressed as a data point. And by the way, these numbers are accurate thanks to my mother and her diligent record keeping. So when we have data like this, we can use it to predict or forecast the future values based on the past observations. Say that I know the prices of corn over the past month. I may be able to use this to predict what will be the price of corn tomorrow. However, in most cases, we need more than one data set to make good predictions. In this XKCD comic, he's just using a couple of data points to predict the future of her marital status. But we can use the same concept and apply it to when we're not looking at enough data sets. We really need to understand how data sets interplay with each other to get the full picture and make better predictions. So I may be able to use my intuition about several data sets and join them together in a way that produces better forecasts. So I have the historical prices of corn, but maybe I believe that the temperatures in the area where corn is produced plays an important role in how corn is priced. If I can join these data sets together, I can learn the interesting relationships between them and use it to make better trading strategies. And since we're meeting in Brussels to do this talk, I figured I'd do the conversions for you. Recall that in a left join, I have 2 tables, and I want to bring all the matching data sets on my right table, on the matching rows, on the right table, together with each row in my left-hand table. When there's no exact match, I return null for that row, but in my joined data set, the joined data set contains every row from the left-hand table. A temporal join is a particular join function defined by some matching criteria over time. So just like with relational databases, I have full outer join, left inner, right outer, cross. I have all these different types of joins. But what makes temporal join special is this look forward and look backwards criteria. So if I want to do a left join on these 2 tables, the first thing I'll do is look for an exact match. If we were doing a regular left join, we'd be done now. There is no exact match, so we'd return null. But I'm able to actually look backwards and find the timestamp on the row that's nearest to the timestamp that I'm looking for. And I can use this to do my join. Note that in these examples, typically when we look at time in a line, we look at it horizontally. But in these examples, I'm looking at time increasing going downwards because it's more reflective of how we look at time in a database with time ascending. So backwards in this case is the data point physically above it on the line. Similarly, for look forward, I look for the exact match on my timestamp, and when it doesn't exist, I look for the next timestamp, and I'll be able to use that to do my left join. In the world of finance, we typically tend to default to look backwards criteria. Once I've analyzed all these data sets and I have a model that I ultimately want to execute on, I'll no longer have the luxury of looking forward because it would be reflective of looking into the future, looking to a timestamp that doesn't yet exist, and we don't have the technology to do that. So we look backwards by default because it more accurately simulates live analysis. So now I'm going to walk through a pretty simple example of this. Let's say that my theory is that the price of a stock called Berkshire Hathaway is directly impacted by the number of tweets about the actress Anne Hathaway. At this point, my legal department would like me to remind you that this talk contains no trading advice. I do not recommend trading on these ideas. Okay, so I have Anne Hathaway tweets, which are sampled every 2 hours, and Berkshire Hathaway prices, which are sampled every 3 hours. So they're unaligned. So I'll need to do what's the temporal left join to bring these data sets together. For the 8 a.m. row, I have an exact match, so I'm able to just do a left join as normal. For the 10 a.m. row, I don't have an exact match on Berkshire Hathaway. So I look backwards and I find the previous row, 8 a.m. of $2, and I'll use that to do my join. Similarly, for 12 p.m., I don't have an exact match, so I look backwards at the 11 a.m. row, and I use this to do my left join. In practice, we may have thousands of these market data sets, and we want to be able to predict what's the price tomorrow, in the next 2 hours, the next 2 seconds, maybe even more granular than that. And I could have hundreds of thousands of data sets with unaligned timestamps. We live in a world with big data, where big data could mean the size of one particular data set or the number of data sets that we're looking at. I mean, it could be ocean tides, commuter information. Practically everything we do has some component of big data now. Our objective is to understand these diverse and divergent data sets, see what their relationships are together, and understand them to ultimately create better investment strategies. These are pretty simple examples with 2 and 3 rows, but in practice, one single data set may be 300 terabytes, which can't fit on a small cluster, let alone a small machine. And I may have hundreds of these data sets, and I want to understand what the relationships are between them. When do they impact one another? When are they not related at all? So with all this data, we need a fast and scalable distributed temporal join. And this is the challenge that we are addressing in this work. The first thing that we did was look at the existing solutions that were out there. What we found was that they either didn't support the temporal join that we needed, or they didn't scale to the level that we needed it to. So with Pandas or R or MATLAB, you can create something to do this temporal join, but it will assume that all your data exists on a single machine. With Spark, the data does scale, but since by its nature, Spark data is unordered, it's not particularly efficient for our use case. Lastly, there's Spark TS, which is another open source library which set out to handle time series analysis. What we found was that it didn't work for our use case for several reasons. So first, it expects that each single predictor, each univariate time series, will fit on a single machine. So as such, it splits the data by column, which makes the tables kind of short and fat, and we really prefer our tables to be long and thin to do all the different types of operations that we need to. Lastly, because of the way that it constructs these data sets that are split by column, it assumes that you have a quasi snapshot of your data. It doesn't really lend itself to incoming streams of data. So for these reasons, we weren't able to use the Spark TS. But the more we looked into Spark, we saw its speed and reliability. So we set out to build a framework on top of it. Originally, we were really just trying to solve for the temporal join problem. But as we've grown, we've built a general purpose library that solves for time series operations. We provide a collection of functions to manipulate and analyze time series data at massive scale. In order to do so, we've built a time-aware data structure that extends RDDs. Again, We know that our data is strictly structured such that it's ordered by time. So we can use what we know about the temporal locality to really reduce shuffling from a logarithmic time operation to just a few per data point. TimeSeries RDD is the data structure that contains a time series. So the main differences between this and a regular RDD are that we associate a time range with each partition. And then as we perform operations, we track the time range as we go. And in the end, we're left with a time series where temporal order is still preserved. If I had a regular RDD and I did a map function and a filter, I can't really be sure what the order of the data would be when I received it back. But with time series RDD, I'm always guaranteed to receive back an in-order time series. So here's a visualization of this. I have some temperature data and time, and if I have a regular RDD, I don't really know how the partitioning will work. I don't know for each row that I'm looking for which partition it will live in, and I don't have any information about the data contained within one single partition. With time series RDD, I associate a time range with each partition. So I know that all my data between 6 and 7 is in the first partition, between 7 and 8 in the second partition, and all the data after 8 in the third partition. In practice, we don't actually break our partitions down by hour, but this is just to show you an example to show you that it's exclusive. Meaning for each partition, it will only contain the data in that time range, and all the data within that time range will live on that particular partition. So let's take a look at a simple grouping function to see the power of using time series RDD over regular RDDs. A grouping function is one of these first natural operations that we like to do on a time series during time series analysis. So I have some data of temperatures between New York and Brussels, and I could do a grouping where I'm grouping on exact timestamps. Another thing I might like to do is group by nearby timestamps. So I could group all the data before 2 p.m. and then all the data after 2 p.m. So let's imagine that I want to do this with a regular Spark RDD. Assume that the data exists in 2 partitions in the RDD, and it's already sorted. If I want to do a group by, I'll call group by on time, and the hash partitioner will effectively shuffle all my data around, and in the end, I'll have something where the data is indeed grouped by time, but the temporal order is no longer preserved. In order to reintroduce temporal order, I'll need to call another sort by. And again, the data will be shuffled around, and I need to materialize the data on each of the workers as I go. So this ends up being pretty expensive, and I have to do these non-local, like inefficient operations several times as I'm doing my time series analysis. So now imagine I have the same problem using a time series RDD. My data is split between 2 different partitions, and I want to group by on exact timestamp. So because I know the data is ordered and local to each partition, I can do the grouping per partition locally. I don't have to pull all the data in at once. I can do this on the fly, on demand, in a streaming fashion. So in this case, I end up with a time series RDD that's still ordered by time and is grouped by time. But this time I didn't even have to use most of the slide. So we ran some performance tests. We had data that was living in Parquet in HDFS, and we ran a group by in pair RDDs and DataFrames versus group in our time series RDDs. And afterwards, we ran a count to force execution in each of the executors. So we had 16 executors, 10 gigs of memory, and 4 cores each. What we found was, as compared to RDDs, we saw a 50 to 100 times speed up. And even as compared to DataFrames, we saw 5 to 10 times speed up. Cha-ching! Okay, sweet. So let's go back to the question from the beginning. How can we use this to create a temporal join? Recall that a temporal join is a specific join function defined by a matching criteria over time. So there's two matching criterias. One we spoke about already, so that's direction. Do we want to look forward or look back? Secondly, we can specify the window. How much do we want to look forward or how much do we want to look back? Let's say I'm looking at my left join example from earlier, and I want to do a left join from the right-hand table to the left. If I select a window that's too small, I won't actually get a data point within that range. But if I can use a bigger window, I'll find the data point that matches my timestamp, and I can use that to do my left join. So let's imagine that we wanted to perform this operation on a single machine. We had two time series, and we want to just do this left join. I can look at the first value in each. I'll see that the 1 a.m. should map to the 1 a.m. I'll look at the second values in each. I'll see that 3 a.m. is after 2 a.m., so I'll still use my previous value of 1 a.m., and I'll do this join. Again, I'll continue on. I'll check that 3 a.m. is within my 1 hour window. It is, so I'll not move forward in the right-hand side yet, and so on. Basically, I have two iterators, and they're keeping track of their previous value and their current value, and I can do this join. We can reason about this pretty simply. So now, how do I accomplish the same thing when I have a time series RDD and the data is split across many machines? I want to do this temporal join in a smarter, more efficient way. The first thing I'll do is I'll partition the time space into two disjoint intervals, in this case two. And then for each of the disjoint intervals, I'll create a joined partition. Recall that I'm storing metadata on each of my partitions, so I know which time ranges exist on that partition. And I can use this metadata to build a dependency graph that knows how to build the joined RDD. So I don't actually have to bring any of the data in onto any of the executors. I can do it on the fly in a streaming way as needed. So let's say that I now want to do a count on my joined partition, my joined time series RDD. So based on my dependency graph, I know that I'll need data from the first partition on the left and right-hand side. And I can pull these in as streams. I don't need to do this all at once. And in my second partition on the joined time series RDD, I know that I need data from the first partition, and so on. So we ran some performance tests on this as well. Remember that we don't actually have a temporal join on RDDs and DataFrames. So we compared it with our temporal join with a window of size 0, in other words, an exact left join. So again, we were reading data from Parquet in HDFS, and we had 16 executors, each with 4 cores and 10 gigs of memory. As compared to RDDs, we saw a 20 to 50 times speed up, and again, even as compared to DataFrames, we saw a 5 to 10 times speed up. So using similar methodologies to temporal joins and groupings, we've created additional types of grouping functions, and we've also been working on additional types of joins. So I mentioned look forward and look back, but we also now have symmetric joins and outer joins and additional types. We've also worked on a bunch of different summarizers. We have average, variance, z-score. We call them summarizers. This is what Spark refers to as aggregators, but these different aggregation functions. And in each case, we can apply the different aggregation functions over each particular group, which is a pretty common thing we want to do in time series analysis. And we are open sourced. So the title in your schedules says OrderedRDD, but we're now called Flint. So check us out on open source. At 2 Sigma, we really value open source. We want our developers to be able to contribute to it and to use open source. So we hope that you will find this useful. This is the URL for the software that I've been describing today. But check out GitHub/2Sigma. and check out some of the other projects that we've been working on. We'd love to hear how you're using it, and please contribute and let us know what you think. Oh, I'm not done yet. Sorry, I'm not done yet. But we should clap for open source. So, coming up, we want to do more integration into datasets and DataFrames. As we all know, in Spark 2.0, there's a lot of cool things and a lot of optimizations that are happening in datasets and DataFrames. So we want to be aligned with that. When we initially started building this software, it was on Spark 1.6. So we've already started this work. And we've also worked on some Python bindings to do more PySpark integration. And we're always working on more summarizers. More summarizers is more better. I'm really happy and lucky to be presenting here today, but this was a lot of work by a lot of people, and I want to give a big thank you to everyone on this list. So, to summarize, Flint. This is our general purpose time series analysis framework, which we've open sourced. Anne Hathaway has nothing to do with Berkshire Hathaway, and please check us out and contribute. Thank you.
Any questions for Larisa? Okay.
Have you considered building some averaging functions for the time series? So if you're always looking back, that might be not accurate. So let's say your price jumps, or whatever your temperature value jumps from 10 degrees to 20 degrees, and you're using 20 degrees just until the jump point. That might be not as nice as doing an average over the time span.
Yeah, so we have a bunch of aggregation functions that we've been working on. So we have average, and you can apply this to different cycles, which then you can merge to your time series. I think there's...
Oh.
Can you plug in your own join function, something like interpolate between the most recent and the next data point?
Can you say that again?
Can you plug in your own your custom join function, like interpolation of the last and the most recent point? Because you mentioned only taking going back and going forward,
okay.
Something like that.
So you're asking, can you put in your own join function that takes the average of the next and the previous?
Yeah, or a weighted average, of course.
Okay. We don't have anything that supports that right now, but please add it to open source if you think that's something that you would want to use. Yeah.
Thank you.
Thank you. Okay, we still have a couple of minutes. If any, oh, right at the back there. Okay, thank you.
Hey, thanks a lot for the talk. It was very interesting. So I'm wondering about your technique, the temporal join that you're doing. How does this compare to, first resampling each time series to have the same timestamps and then do the simple join? How is this different from this temporal join that you're doing looking backwards? Is there any advantage, disadvantage for one or the other technique?
So you're asking about basically changing the timestamps on your data set and then doing a regular left join?
Yes, exactly.
Yeah, so you can do that. I mean, that would give you the same results, but it's a slower operation. You have to change every single row, and then you either have to maintain the old version or you are no longer able to access that timestamp. So this really preserves your data set, and you can still do this look backwards, look forward join. So it should be faster.
Hey, just a here. I'm
here. Hi, thank you.
Hi. Just a quick question. Once you finish doing your temporal join, kind of the next step would be to find some correlations or something, compute correlation functions or something. Do you have something, some functionality like that in your RDD, or how do you proceed then?
Right, so once you have the temporal join, you have a multivariate data set, so you can proceed to do your time series analysis as you would otherwise. So we have different aggregators and different functions that you can use and try and understand the relationships between your data.
Okay, I think time for one more question. Let's,
Hi, thanks for the talk. How does the temporal join perform when the window needs to be very big? So you basically need to join everything with everything.
When the window is very big?
Yeah, so you need to join, the previous sample has been like a year ago, so your window needs to be very big to look back.
Right. Well, so it doesn't necessarily mean that you have to look backwards. Again, so because we're building the dependency graph, if your last data point is like several partitions above, it's still just as fast as if it were in the partition above. So because we're using this dependency graph to actually do the temporal join, it shouldn't be a hit.
Thank you.
Yeah. Okay. Thank you very much.
okay, thank you.